Hey everyone, and welcome. Today we're going to talk about something that, literally holds our world together, gravity. We're going to peel back the curtain and look at the elegant physics behind everything from a dropped pen to planets zipping around the sun. So let's jump in. So here's our game plan. First, we're going to smash a super common myth about how things fall. Then we'll get on the same page with the language of gravity. After that, we'll look at the surprisingly beautiful symmetry in an object's flight path. Then, believe it or not, you're going to become an experimental physicist in your own home. And finally, we'll see how scientists calculate the Earth's gravitational pull with incredible precision. All right, let's kick things off with a question I bet you've wondered about for ages. If you took a heavy bowling ball and a light little feather and dropped them at the exact same time, which one would win the race to the ground? I mean, your gut probably says the bowling ball, right? It just feels heavier, so it should fall faster. But is our intuition right on this one? Let's find out. So what does physics actually have to say about this? Let's dive right into our first section and get to the bottom of this mystery. Okay, so here's the big secret, the core principle right here. If, and this is a big if you can get rid of things like air resistance, then it doesn't matter what an object is made of or how much it weighs, everything falls with the exact same acceleration. And this isn't just some textbook theory, it actually happened. When astronaut David Scott was on the moon, where there's no air, he dropped a hammer and a feather. And guess what? They hit the dusty ground at the exact same moment. Mind-blowing, right? Now, to really get a grip on this, we've got to make sure we're all speaking the same language. The language of physics, that is. So let's lock in a few key terms. First up is free fall. Now, in the physics world, this is kind of our perfect, idealized scenario. It means an object is falling with only gravity pulling on it. We're just going to pretend for a minute that air resistance and friction don't exist, so we can see what gravity is doing all by itself. And that constant pull from gravity, it causes a constant change in speed, which, as you know, we call acceleration. This specific acceleration is so important in physics that it gets its own special symbol, a lowercase g. Here on Earth, the average value for g is 9.80 meters per second squared. But what does that actually mean in plain English? Well, it means for every single second an object is falling, it speeds up by 9.80 meters per second. So after 1 second, it's going 9.80 meters per second. After 2 seconds, it's traveling at 19.6 meters per second, and on and on. It's a steady, predictable increase in speed. Okay, this next part is super, super important, especially if you're working on physics problems. Is g positive or negative? Well, guess what? You get to decide. It all depends on the coordinate system you set up. If you decide that up is the positive direction, then gravity, which pulls everything down, has to be negative. But if you want down to be positive, then g is positive too. It doesn't matter what you pick, as long as you stick with it for the whole problem. All right, theory's down, terms are defined. Let's put this stuff to the test with a classic scenario, throwing a rock off a cliff. So, picture this. You're standing at the edge of a tall cliff. You take a rock and you throw it straight up into the air. Let's say it leaves your hand going 13.0 meters per second. Now, just to keep our work tidy, we'll call the cliff top our starting point, y equals 0, and we'll say up is the positive direction. So let's follow the rock's journey. After 1 second, it's still heading up, but see how gravity has already slowed it down? Then, at 2 seconds, look at the velocity, it's negative. That's the turning point. The rock has hit its highest point and is now falling back down. But now look at that last column. The acceleration, it's the same, always, negative 9.80. It doesn't matter if the rock is going up, down, or is at the very top. It never changes. And this brings me to one of the biggest mix-ups I see students make all the time, so listen close. People think that at the very top of its arc, when the rock stops for just a tiny instant, its acceleration must be 0 too. But nope, think about it. If acceleration was truly 0 at that point, the rock would just float there forever. Gravity doesn't take a coffee break. It is always pulling down, constantly accelerating the rock at negative 9.80 meters per second squared, even at the very peak. Okay, so what if we switch things up? Same cliff, same rock, but this time, instead of throwing it up, we throw it straight down with that same initial speed of 13.0 meters per second. What do you think happens now? And check this out. This is where physics gets really elegant. It doesn't matter if we threw the rock up first and let it fall, or just threw it straight down. By the time it reaches that specific point below the cliff, its velocity is exactly the same. This shows a beautiful symmetry in physics. The final speed at any given height only depends on the initial speed you gave it, not the direction. How cool is that? All right, enough with the cliffs and imaginary rocks. Let's bring this physics right into your living room. Seriously, you can actually use what we've just been talking about to measure your own reaction time. You've probably seen this one before. It's a classic for a reason. Grab a friend and a ruler. Have your friend hold the ruler so the bottom edge is right between your open thumb and finger. When they drop it with no warning, your job is to snatch it as fast as you can. The distance the ruler fell before you caught it tells you everything. You can use a kinematic equation to calculate exactly how fast you reacted. Go on, give it a try. So that ruler drop is a fantastic little home experiment, right? Well, it turns out physicists do a much more precise version of that same basic idea to figure out the value of g in the first place. So how do we actually pull g out of an experiment? We start with one of our trusty kinematic equations. Now, if we just drop an object from rest, its initial position and initial velocity are both 0. That makes our lives way easier because a bunch of terms in the equation just vanish. We're left with this much simpler version. And with just a little bit of algebraic shuffling, we can get a, the acceleration we're looking for, all by itself. So let's plug in some super precise numbers from a real lab. Let's say an object falls exactly 1 meter, and we time it with a very accurate clock. We pop those values for distance and time into our new formula, run the calculation, and what do we get? Boom, negative 9.8010 meters per second squared. That's an incredibly accurate measurement of Earth's gravity, and we got it just by dropping something and timing it carefully. And really, that's the big takeaway here. The way things fall isn't random or chaotic. It follows these clear, consistent, and honestly beautiful mathematical rules. And once we understand those rules, we can not only describe what happened in the past, but we can accurately predict what's going to happen in the future. So, to wrap up, I'll leave you with a little puzzle to think about. An astronaut can jump with a certain amount of oomph, a certain takeoff speed. Now, we know the moon's gravity is way weaker, only about 1/6 of Earth's. So with that exact same takeoff speed, how many times higher could that astronaut jump on the moon? Think about the physics we've discussed. I bet you can figure it out. Thanks so much for hanging out and exploring the physics of falling objects with me. Hopefully, the next time you drop your keys, you'll take just a half second to appreciate the incredible, predictable math that's at play. Keep asking questions, and we'll see you in the next one.